Good afternoon, everyone. Today we're going to do a video on integrating by substitution. So this is typically one of the first methods we learn to work with integrals. We're going to go through two examples in details and hopefully cover any kind of tricky parts to it that might be causing some grief. So for our first example, we have the integral of x cubed all over 3x to the 4 plus 1. So our first task is to choose some part of the function to make a substitution for u, okay? Now, oftentimes what we're looking for in this step of the process is what part of the integral could we differentiate and find the resulting derivative in another part of the integral. Now that might sound a little funky, but I'll show you what I mean. If we choose the entire denominator of 3x to the 4 plus 1 for u is 3x to the 4 plus 1, what we'll get is if we differentiate du with respect to dx, the derivative of this with respect to x is simply 12x cubed, right? Using our power rules that we learned a while ago, hopefully. We get du dx is equal to 12x cubed. And now what we want is, in our new integral, we'll have, with respect to du, since we're gonna work with our new w variable. And so if we want du by itself, we can kind of think of over dx the same way that we think of any quotient with algebra. We can kind of think of multiplying both sides by dx, and then the dx cancel each other out. This is a crude way of looking at it, but in any case, we will get the result that we need. We get that du is equal to 12x cubed times dx, okay? Now, I'll bring you back to the very start. What we have in the numerator is x cubed times dx. Here we have a 12x cubed dx, okay? So what we would like is we'd like a substitution for what we actually have inside of our integral. And what we have inside of our integral is just this part. We have the x cubed times dx. And so if du is equal to 12x cubed dx, and we only want this part, because that's what we already have, then we can simply divide both sides by 12. And so we get that du over 12 is equal to x cubed dx, okay? And now we're ready to actually make our substitution into our integral with respect to u. We have our du, and we have that du over 12 is equal to x cubed dx. Now, that x cubed dx, we're going to substitute it. We're going to replace x cubed dx with du over 12. And so we're going to have du over 12, okay? And now everything inside, all that will be left in the numerator would be a 1. There's nothing else in the numerator anymore. X cubed dx was replaced with du over 12. And the denominator, 3x to the 4 plus 1, that's precisely u. And so we simply have 1 over u times du over 12. Now, with one of our basic integral rules, we can pull the 1 over 12 outside, because that's the constant. So we have 1/12 of the integral of 1 over u du. And we know how to integrate this. This is a fairly simple integral to evaluate. We'll have 1 over 12 times the ln of u plus c, okay? Now we have our result in terms of u, but we need to finish it off by going back into x. And so if we do that, we could simply plug in 3x to the 4 plus 1 anywhere we see u in our solution. And so we'll replace the u with 3x to the 4 plus 1. And so our final answer will be 1/12 ln of 3x to the 4 plus 1, and then plus c, okay? We don't have to take the absolute value of this part, which is something you will run into in future examples, because 3x to the 4, x to the 4 is an even power, and so this is always going to be positive, and then adding 1, this function will always be positive, and so we don't need to consider the absolute value, because we can only evaluate ln for positive values, but 3x to the 4 plus 1 will always be positive because of what we just talked about. This is always greater than 0. And so we don't need to consider the absolute value. And so this is our solution, okay? So again, look for a part of the integral that you can make a substitution for, where when you take the derivative, the other part of the integral becomes spoken for, okay? So we took the denominator, the entire denominator, we made that u, and then du differentiated to become essentially what was in the numerator, which made our lives much easier when we made a change of variables. And then once we came back to x, everything was fairly straightforward, okay? That's typically how these solutions tend to look. So, for example 2, let's make a nice division here. We have the integral of sine x cos squared x, okay? Now, what we do know, off the top of our heads, is we know that d dx of sine x is equal to cos x, and similarly, we know that d dx of cos x is equal to negative sine x. Okay, we have to remember our basic trig derivatives. And so, if we're again looking for change of variables, substitution, for something in here that when we differentiate it takes care of the rest of the stuff inside the integral, a likely candidate would be cos x. So if I go ahead and make that substitution of u is equal to cos x, okay, then we need to consider what dx is going to become when it changes to du. And so du is going to be the derivative of cos x, which is negative sine x, and dx, okay? Now, if I attempt to write this new integral with respect to u, what we'll have is cos squared x is going to become u squared, right? Because if u is cos x, then cos squared x, that's going to be u squared, right? So we'll have u squared, and then the other stuff, the sine x dx, that's pretty much what we get out of du. The only little change is that we have the negative here, and so if we want just sine x dx, we can, since du is negative sine x dx, then we can equivalently write that negative du is equal to sine x dx. Okay, and sine x dx is exactly what we have in the first step of our integral. And so now we can replace sine x dx with negative du. Okay, that's going to go ahead and replace that. And so now, instead of sine x dx, we'll simply have negative du. Okay, and then we can think this a little bit. That negative can go out front because that's just like a constant of -1. And so we have negative the integral of u squared du. And that's about as easy as it gets in terms of integrals. And so we have equals negative u cubed over 3 plus c, because when we're integrating, we always have to consider that arbitrary constant at the end. And now, going back into our original variable x, since u is cos x, let's replace u with cos x at the very bottom. And so we'll have negative cos cubed x over 3 plus c for our solution. Okay, so again, our process is typically very similar in that we look for a part of the integral that we can make a nice substitution for, which is where the u is equal to cos x comes in, because we know that cos squared x can be easily written as u squared. And then we want to pick a part of the integral that when we differentiate it, the other stuff inside the integral becomes spoken for, which is what we see here. The sine x dx kind of gets taken along for the ride through that differentiation process in our substitution of variables, okay? So again, try to go through as many practice questions as you can. You'll get a feel for which parts of the integrals are the best candidates to substitute for. And this becomes a really, really important technique in iteration. I hope this helps. I hope this provides some clarity. If you have any questions, comments, suggestions, please let me know. Any questions for these videos are always appreciated. And thank you so much for watching.